Have you ever stopped to question, what is the true nature of reality? This is not just a philosophical musing, but rather a scientific inquiry that has been at the heart of human curiosity for centuries. We live in a universe that is full of wonder, a cosmos so vast and complex that it often defies our understanding. From the largest galaxies to the smallest particles, everything we know, everything we perceive is part of this grand tapestry we call reality. Over time, our understanding of reality has evolved significantly. From the ancient Greeks who believed in the existence of four basic elements, earth, water, air, and fire, to the modern scientists who have discovered that everything in the universe is made up of fundamental particles, we have come a long way. Today, we live in an age of quantum mechanics and relativity, where we understand that particles can exist in multiple places at once and that time itself can bend under the influence of gravity. But as dazzling as these theories are, they are not without their limitations. Quantum mechanics, for instance, works wonderfully well when dealing with the tiny world of particles. But when it comes to explaining the larger world of galaxies and black holes, it falls short. Similarly, Einstein's theory of relativity does a remarkable job describing the universe at large scales, but fails when it comes to the world of the very small. Clearly, there are gaps in our understanding. There are questions that remain unanswered. What is the true nature of reality? What is everything made of? How does the universe work at its most fundamental level? To answer these profound questions, we need a more comprehensive theory, one that can reconcile the world of the very large with the world of the very small. We need a theory that can bridge the gap between quantum mechanics and relativity, between the world of particles and the world of galaxies. Enter the world of string theory, a theory that promises to answer these profound questions. So, what exactly is string theory? A question that has been puzzling the greatest minds of our generation. String theory, in its most simplified form, is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. In traditional particle theory, particles are viewed as zero-dimensional points. Imagine a particle as a dot on a piece of paper. It has no length, width, or depth. It merely exists at a single point in space. This view has served us well in explaining the behaviors and interactions of particles, but it also comes with its set of limitations and paradoxes. Enter string theory. String theory takes the concept of particles and stretches it, quite literally. Instead of viewing particles as zero-dimensional points, string theory proposes that particles are actually one-dimensional strings. Picture a particle not as a dot, but as a tiny vibrating piece of string. This string can wiggle and oscillate, and it's these vibrations that give the string, and hence the particle, its properties like mass and charge. One of the most beautiful aspects of string theory is its inherent symmetry and elegance. It's like a symphony, with each string playing its own note, creating a harmonious melody that forms the reality we experience. But how does this differ from traditional particle theory? Well, where particle theory struggles with inconsistencies between quantum mechanics and general relativity, string theory potentially reconciles these two conflicting theories. It does so by providing a framework that naturally includes quantum gravity, a unification that has been the holy grail of theoretical physics for decades. In essence, string theory opens up a whole new way of understanding the universe and the fundamental laws that govern it. It's not without its controversies and challenges, but it offers a promising avenue for unraveling the deepest mysteries of the cosmos. And so, in string theory, it's not particles that form the building blocks of the universe, but these tiny, vibrating strings. Now, imagine a universe where these tiny strings are the fundamental constituents. This is the universe according to string theory, a universe where every particle, every force, every element of matter we know, down to the most minute detail, is comprised of unimaginably tiny strings of energy. These strings, vibrating in different ways, give rise to the diverse particles we observe in our world. Picture this. You're at a concert, listening to an orchestra. Each instrument, though different, is essentially made of the same thing, strings. And it's the way those strings vibrate, their frequency, their amplitude, that creates the unique sounds of a violin, a cello, or a bass. In much the same way, the universe of strings vibrates. Each string oscillates at a distinct frequency, and these oscillations produce the plethora of particles in the universe. A string vibrating at one frequency becomes an electron. At another frequency, it becomes a quark, the building blocks of protons and neutrons. But what about the forces that govern these particles? You guessed it. They too are made of strings. The force of gravity, electromagnetism, the strong and weak nuclear forces, all are the result of strings vibrating at particular frequencies. And the most fascinating part? These strings are not just vibrating in one dimension but in multiple dimensions, some of which are beyond our current perception. This multidimensional dance of strings gives rise to the complexity and diversity we see in the universe. From the tiniest particles to the vast expanse of the cosmos, everything is interconnected, linked by the symphony of strings. Each string, a note in the cosmic melody, playing its part to create the grand orchestra that is our universe. And so, string theory gives us a new way to perceive the universe. Not as a collection of separate particles and forces, but as a dynamic, interconnected web of vibrating strings. So, in essence, the universe is like a grand symphony of strings. But string theory doesn't stop there. It also introduces the concept of extra dimensions. Think about the world around you. You can move left or right, forward or backward, up or down. That's 3 dimensions. Add time into the mix and we live in a 4-dimensional reality. But according to string theory, this isn't the whole picture. Let's dive a bit deeper. String theory suggests that the universe is not 4-dimensional, but rather 10 or even 11-dimensional. These aren't dimensions in the sense of parallel universes or alternate realities, but rather additional spatial dimensions that are compactified or hidden from our perception. Imagine a tightrope walker. To them, the rope is essentially one-dimensional. They can only move forward or backward, but if we zoom in, we'd see that the rope is actually 3-dimensional. It has length, yes, but it also has width and depth. The tightrope walker doesn't notice these dimensions because they are so small compared to the length of the rope. Similarly, the extra dimensions proposed by string theory are so compact, so tightly curled up, that we don't notice them in our day-to-day lives. Why would string theory need these extra dimensions? Well, in order for the mathematics of string theory to work out, these additional dimensions are necessary. They provide the room for strings to vibrate in various ways, producing the different kinds of particles we observe in the universe. It's a mind-bending concept, isn't it? The idea that there could be more to the universe than what we can perceive. But that's the beauty of string theory. It opens the door to a universe far more complex and fascinating than we ever imagined. The extra dimensions of string theory, hidden from our perception, add another layer of complexity to our understanding of the universe. So, what does string theory mean for our understanding of reality? String theory, in its essence, is a theoretical framework within which the point-like particles of particle physics are replaced by one-dimensional objects called strings. It's like swapping out the building blocks of Legos for a piece of thread. This shift in perspective could potentially unify 2 major pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics, the rulebook for particles at the smallest scales, and general relativity, Einstein's theory of gravity that governs the largest scales, have been like oil and water in the realm of physics. They simply don't mix. Yet, if string theory proves correct, it could be the bridge that reconciles these seemingly incompatible theories. Imagine a world where quantum mechanics and general relativity are not at odds but are rather 2 sides of the same coin. That's the promise of string theory. However, it's essential to remember that string theory remains unproven. It's a beautiful, elegant theory, yes, but it also poses immense challenges. For one, the strings in string theory are incredibly tiny, much smaller than anything we can currently observe. This makes experimental verification of the theory incredibly difficult. Moreover, string theory predicts the existence of more dimensions than we currently observe, 10 or 11 instead of our familiar 3 of space and 1 of time. Testing for these extra dimensions presents another huge challenge. Despite these obstacles, research in string theory is ongoing. Every day, physicists around the world are working to refine the theory, develop new mathematical tools, and devise ingenious experiments to test its predictions. The journey towards understanding our reality is far from over. But string theory, with all its beauty and complexity, offers a promising path forward. It paints a picture of a universe that is far more intricate, far more interconnected, and far more fascinating than anything we've ever imagined. While still unproven, string theory holds the promise of revealing the true nature of reality, a reality far more intricate and fascinating than we ever imagined.